Good afternoon, students. Hope you are doing well. Okay, so in the morning theory class, we are seeing about various production functions, right? As well as we are seeing about the functional forms of regression. Okay, something was telling us they were much the same, though in production function the objective is different. Okay, so among the things that we're discussing, we were discussing more on the growth model, right? Because in your research in MSc or PhD, you'll be focusing on growth models more and more. Basically, if you take any MSc thesis or PhD thesis, the first objective is going to be estimation of growth trend of any macroeconomic indicator. It can be area, production, productivity, and we're interested in getting to know the growth trend of that variable, right? So this growth estimation can be done using a model. That model is called as growth model. Okay, and we know that this is called as log-lin model. So this log-lin model is also called as growth model. In any model or any functional representation, what we have is we have a dependent variable and we'll be having many independent variables, basically, right? So we'll be having a dependent variable and many independent variables. So dependent variable is usually represented by y, okay, and the sign of independent variable is x, right? So this is log-lin variable. It means what? The y, that is the dependent variable, we are taking log of all the values in the dependent variable, and in the case of independent variable, if you have got only one independent variable, then we are using it as such. We are not transforming it. So this is what is called as log-lin variable. That is taking log of the values of dependent variable and using the values of x, that is independent variable as such, right? So this is what is log-lin model. So if you could see PRF, that is population regression function, in the case of log-lin model, it is yi is equal to beta 1 e to the power beta 2 xi, then e to the power ui. So this is what we know is error term. So this separates econometric model from that of a mathematical model. So what is happening in the case of a mathematical model where we have only y and x, we don't have this error term. So this is error term, right? We should know what error term is. We should know what is error term, what is standard error, and what is the standard deviation. So all are different. So what is error term, right? For example, this is we are including. We are trying to say in this equation that x is an independent variable. This is influencing y. So we'll be able to find what is the average effect of x on y. So this is what we are going to find, because this y is dependent on x. Okay, so this x can be used to capture the changes in y. So the x will influence y. So this is the model. At the same time, even though we have xi, right? So I can be 1 to 100. If we have hundreds of independent variables, there can be some other variables also which we have not included in the model, but certainly they might be having effect on y. So they may influence changes in y. So this error term represents all the other variables which we have not included in the model. So that is captured by the error term. This we know very well, right? So the lesser the value in the error term, the more robust is the model, and we can say the changes in y, the better can be explained by the x variable. Okay. So now if you could see this equation, and now if you are able to see this one, okay, which I'm showing it here. So we are taking log on both sides. So ln, we know very well is natural log. Okay, so natural log is what? Log e. And if we have log, it means log base 10. That is different, right? So what is log actually? I think we might have seen, right? If you're thinking about log 10, so if you have a value like 746 hectares in one particular taluka, let us say Vantali taluka, 746 hectares of groundnut. So if you want to find log of that 746 hectares, then if you are using log base 10, so 10 raised to the power of what gives you 746, the value is 746. That is what is the log actually, right? If it is log e, then e raised to the power of what? E raised to the power of what gives you that 746. So that is what is log e, okay, natural log. And this is log 10. So this is natural log, right? ln. So if we're taking log 10, then we had to use log log, okay? So we are taking log on both sides. So here, this is the left-hand side, LHS, this is right-hand side. So log yi is equal to log beta 1 e to the power beta 2 xi, then e to the power ui. So then on further processing, what we have is we have log beta 1 plus beta 2 xi plus ui. Here we could see clearly that here in the case of independent variable, there is no log present over here. So whatever values we have, we are using it as such without transformation. But on the other hand, if you could see dependent variable, it is log yi. So we have to transform the values in the dependent variable to in logarithmic format. Okay, so this is what log yi is, and here we're using as such. So now how to interpret now? If you interpret, so in the case of a linear regression, what we will do, if there is no log over here, it is simply yi is equal to whatever it is, beta 1 plus beta 2 x. Then what we will do, if x changes by 1 unit, y changes by so and so unit. That so and so is captured by the slope. So this slope, in case of population, it is parameter, right? So this parameter, or in case of we have had over here, right? So this is what sample, right? So this is PRF and this is SRF, sample regression function. So if you are using sample data, we can call this a statistic, right? So let us assume this is population data because we have derived from secondary data source. So if it is population data, this is parameter. So if the parameter is 0.4, right? So f increases by 1 unit, y increases by 0.4 unit. So that is what the interpretation in the case of a linear regression. But what we have here is, again, we have linear regression, but the format is different. The format is log-lin. This is also linear. Why it is linear? Because here you could see the variable is linear because it is raised to the power 1. At the same time, you will see parameter. This is also linear. So you can say an equation is linear when the parameter is linear. The parameter is linear. Forget about the variable. The necessary condition is the parameter should be linear. Here you could see this is raised, this parameter beta 2 or the slope parameter or the slope, it is raised to the power 1. So it is linear, right? So now how to interpret this? Because we don't have a simple y over here, we have log, natural log yi. So it means what we can interpret, if x increases by 1 unit, y increases by beta 2, that is slope coefficient times 100%. If this is 0.4, okay, then if x increases by 1 unit, y increases by 40%. Are you getting it? So this is how we have to interpret. You see here, if x increases by 1 unit, y increases by beta 2 times 100%. So this is what the interpretation of a log-lin model. In this way, we'll be able to understand about the growth. For example, in x, we are taking time period, and in y, we have area, for example. So the time period is from 1986 to 2010. So from 1986 to 2010, when we have taken, if the beta 2 is 0.4, then we can say that area has increased by 40% over the time period. And here 40% per annum, right? That's very important, okay? 40% per annum. Okay, so that is what we mean to interpret in the case of log-lin model, right? Now, let us proceed further. Now, so why we call it growth model? Because in growth model, we'll be able to understand magnitude of the rate of change of variable. Whatever variable you are taking, whether it is area, production, productivity, whatever variable you are taking, you are finding the magnitude. What is the amount of change? What is the quantum of change? What is the level of change? But in growth rate, as we would have seen the literature, we have magnitude as well as direction, because the symbol is negative. We can say negatively, negative growth rate. If it is positive, we can say growth rate. If it is negative, we can say negative growth rate. And then we have the magnitude also, the amount. So in growth rate, we have the direction as well as the amount, right? Now, the principle is simply compounding, right? What is compounding? Over the time period. For example, if you have got 10,000 rupees in your hand right now, what you're doing is you're depositing in bank, say the nearby SBI, State Bank of India, you're depositing your amount in savings deposit, for example. So the interest rate is very less, right? 2.7%, for example. So over the time period, what will happen? The interest will keep on adding to the original amount. So if you're taking your amount after 10 years, then whatever the interest is, then we have number of time period, years, accordingly you'll be getting the money. So compounding will help us in understanding what is the future value of present money. At present, if I got 10,000, after 5 years, what is the future value of present money? So that you can find by how, for example, here you can have FV, future value is equal to present sum, then 1 plus I to the power n. That is compounding formula, right? So I is the interest rate, and T is the, or N is the time period, or T is time period. Similarly, what we have is, here we have what is final value. This is the initial value. Then 1 plus R. R is the growth rate, and T is the time. So we can apply the same principle over here, principle of compound, right? Here, the thing is that in growth rate, in the previous case, what we have seen, okay, for example, here we have interpreted, right? That is, if X increases by 1 unit, Y increases by this slope coefficient times 100%, right? So this is called instantaneous growth rate. This will tell you growth rate at a point of time. But in our case, when we do MSc research and all, now, when you are doing MSc research and all, any paper, when you want to write, then we are more interested in finding the compound growth rate. So over the time period, what is the growth rate? So that, for example, I'll be telling you how to do it, but both things can be done, instantaneous growth rate as well as compound growth rate, okay? So accordingly, for further processing, what you're getting is, you see here, the equation when you're taking log on both sides, what we have is log yt is equal to log y0 plus t. You see t is the x variable, independent variable, log 1 plus r. So this log 1 plus r, entire thing is beta 2. So t beta 2, okay? And then what we have log y0. It means log beta 1. Okay, when we have that, you can have this equation. So log beta 1, then beta 2 xi plus ui. Similarly over here, we have log beta 1 plus here t, then beta or beta 2t. Okay, in whatever we want to say. Okay, just a minute, I'm getting a call now. I'll call you. Just let me stop now for just a second or two. Okay. So that was an urgent call from the placement cell. Okay. Now what we are talking about, the principle of compounding, right? Now you would have understood. At the same time, we also know the discounting principle, the opposite of compounding, which will help us understanding the present value of future when discounting, especially in agriculture projects and all, right? Wherever we have investments, we deal with discounting, because at present we don't have any money. We are going to get money after 5 years. After 5 years, whatever money that we are going to get, what is the present value of future money? That is discounting. For example, right now you're studying MSc, right? You entered the job market. After 3 or 4 years, you are getting a good job. You are making career. And then you're getting a salary of, for example, 75,000 rupees per month. That's your salary, first month salary, okay? Then the salary which you're going to get after 4 years, 75,000 rupees per month. What is the present value of it? So that is what discounting is. Here, what is the future value of present money? Right now we have money. What is the future value of it? Okay. So upon further simplification, we can understand that the compounding principle is applied in the growth rate. Okay. Now, as I told you, using this log-lin model, we can understand instantaneous at a point of time. That is, when we solve the equation, when you obtain the slope coefficient, that is beta 2, we can give it any name. It can be alpha, beta, gamma, it can be omega, it can be simply A and B, it doesn't matter. As I told you, Greek letters, we are using it because it is fanciful. Looking at Greek letters, we should not be terrified, because that is what the case is. It makes the equation unique. If you can make something like this, y equal to a plus bx, but that is it is not unique, right? It looks very simple. Let us complicate it further, so as to think that we are doing something good. It's a kind of, how to say that, if you're using Greek symbols over there, it gives you some kind of edge over it, that you're doing something good. Or when you are discussing many things, right, even interpretation, when you're using those Greek letters, that will help you to separate your text from the equation, right? And because if you're using y equal to a plus bx, and then when you're discussing, because in thesis as well as in your exam answer sheet you should discuss, right, then there are chances for you to do mix-up. So to avoid all those mix-ups, if you're using some Greek letters, that will be good. That is what the tradition is. It separates the equation from the text. That is the ultimate purpose that we can understand, okay, in that way. Okay, now, so as I told you, we can go for instantaneous growth rate as well as compound growth rate. Now the thing is that instantaneous growth rate can be obtained by, as I told you, by multiplying the slope coefficient by 100 times, and we can interpret if x increases by 1 unit, then y increases by the slope coefficient beta 2, as the case was, into 100%. But now how to find the compound growth rate? Again, we have beta 2, right? We have to do anti-log. So anti-log of the estimated beta 2. Using the regression equation, we have estimated beta 2. slope coefficient, take the antilog of it, and then subtract 1 from it, then multiply by 100. As you can see over here, log b is equal to log 1 plus r. This you know very well, right? So antilog of log b is equal to 1 plus r. Then r is nothing but antilog of log b minus 1. Then c here is given by antilog of log b minus 100. Now, how to take this antilog? Now, if you want to take antilog, in the case of ln, natural log, you can obtain antilog by simply in Excel, you type exp. So you go to Excel sheet, MS Excel, and then you insert equal to, is equal to, then exp, then take that slope coefficient, beta 2 value. Then that gives you antilog, exp. That exp can be used. Now, in the case of log base 10, what you can do is you can use power, POW here. So equal to POW power. Then what is the base we have used? 10, right? So base 10, then comma, the value of the slope coefficient. So that will give you antilog of it. I'll be telling you in Excel sheet, but right now understand this is how we can do antilog. Simply by exp in the case of natural log, and the case of log base 10, log base 10, we can go for power function. Okay. So in this way, we'll be able to find out. So now, right now, what we understood is, we have understood log-lin model is also called as growth model. And log-lin model can be used to find not only compound growth rate, but also instantaneous rate of growth. And we know how to interpret. If in the case of instantaneous growth rate, that is, we are not interested in finding the common growth rate. Simply, we can say if x increases by 1 unit, then y increases by the slope coefficient times 100%. Now, in the case of compound growth rate, we should introduce the concept of compounding. That we know what compounding is, right? We have known right from UG onwards. I would have taught you in 6th semester course, as well as in 3rd semester course, like agriculture marketing and prices, even in production economics, when we are analyzing about the techno-economic feasibility of a project. There now we would have seen compounding as well as discounting measures, right? This is not discounting, that is something else. I was just telling you the difference between the compounding and discounting, but right now we know what compounding is. The same principle is applied in the case of a growth rate. Okay, then we know about the how to derive this, how we are deriving it and how the equation is. Hope you all know what to do now, right? Now let us proceed further. Now the most important thing comes, precision of the estimates. Now, right now, the compound growth rate is 30%. If that is 30%, very good, but that is not sufficient for us. We should know how to, estimate the standard error of it. The standard is very important because that will tell us whether the growth rate is significant or not. If it is 30%, it has to be significant, right? But if it is not significant, then what is the use of a higher value of growth rate? The growth rate, however higher or lower, it has to be significant. We know in econometrics, what we do is we test significance at 3 levels, right? First, 1% level of significance, 5%, and 10% levels of significance. So that is what we do. And we know how to test the significance and all. We can use t-statistics or we can go for p-value. If we go for p-value, we know what to do, right? If the p-value lies between 0.00 to 0.01, that is 1% significant level, right? Then 0.011 to 0.05, that is 5% level of significance. Then 0.051 to 0.10, that is 10% significant level. Then we can look at t-statistics. In t-statistics, then depending on the degrees of freedom, you have to see. Here we are using n-2 degrees of freedom. Why n-2? Because n minus k minus 1. What is k over here? The number of variables. We have only one independent variable, right? So n-2. So we have to calculate t-value first. And then we have to compare our calculated t-value with that of a table t-value. Okay. So when we are calculating, how to calculate? Simply growth rate that you have obtained in percentage divided by standard error of growth rate. We have to estimate the standard error of growth rate. But usually what you are doing, you as well as the seniors, you are estimating the standard error of the slope coefficient. And that you are using as standard error of the growth rate. And then you are coming to a conclusion whether growth rate is significant or not. No, that is not right. Since we have estimated growth rate, we need to also estimate the standard error of growth rate. That is the only solution now. I'll tell you how to do it. You see, the formula is very simple. It looks complex? No. You see, one by one, if you could see, now the formula is very simple. 100 beta hat. Why hat? Because we're using SRF. Okay. What is beta hat doing here? This is the anti-log of log B. So anti-log of log beta hat is your beta hat. Then what we have is log 10, log E. That is log base 10E. The value is given over here, 0.4343. So this is solved since we have estimated, the slope coefficient log B, and then we have to find the antilog of log B, and that antilog of log B will give you this beta hat, right? So 100 into antilog of log B divided by log base 10E. Then you see this one. This one is very simple. Okay, what we have log Y, and then we have T, and then we have beta hat, and then we have N. That's it, right? We have only 4 items. So it is log, here we see summation of log Y squared. This is summation log Y whole squared. Both are different, right? So it means what? We know what log Y is. We have the Y value, and then we are taking the log Y of it, not natural log. We are taking log base 10, log Y of it. Okay, so one column log Y, the second column that you have to make log Y. Okay, then when you have done that, then we should go for third column log Y squared, because it is summation of log Y squared. So third column log Y squared. If you have got 10 observations, then you have to do 10 rows of log Y squared, which you will have 10 rows of values. Then do summation. So summation of log Y squared. Here it is summation of log Y whole squared. Is what? There is no need for you to go for log Y squared. We have log Y, right? After we have 10 observations of log Y, then do summation of log Y, right? Then summation of log Y whole square. That's it. If we are able to know that difference, then it's very simple. Then similarly, we have to go for a summation of T squared. It means what? Like T, what is T over here? The time period, right? If you have got 10 observations, you have got 10 time periods, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is T squared. That is after T, go for another column, T squared column, right? So summation of T squared, then summation of T whole squared. When you do that, and then you will be obtaining standard error of G, growth rate. So we have growth rate, and then we have standard of growth rate. And then in this way, we'll be able to obtain the calculated T value. Once you have calculated T value, you compare that with the table T value. When you compare that, we have to reject null hypothesis. What is null hypothesis? The growth rate is not significant. If that's a null hypothesis, then you have to reject it. So rejecting at, you can reject at 3 levels, whether 1%, 5 or 10% levels of significance that you do, and this is taken care of. This will help in precision of the estimates. That is whether the growth rate obtained is significant or not, that we can see. Okay, now as I was telling you, we should understand error term, standard error and standard deviation, how they are different. First error term, as I told you in the previous discussions, that this error term represents all those variables which are omitted in the model. Okay, the effect of all the omitted variables will be captured by the error term. Okay, so this is error term. Then standard error is what? It refers to the average distance that the observed values deviate from the regression line. We have a regression line. Okay, and in the regression line, we'll be having most values on the regression line or near the regression line, right? Or around regression line, but somehow some values which we observe, they deviate from the regression line. So that is what standard error is. If the deviation is more, then the standard error will be more. Then the model will not be robust. Okay, the standard error should be as much as less as possible. This will help in robustness of the model. At the same time, we'll be having significance of the coefficient. If the standard error is more, then the coefficients may not turn to be significant. Why? Because significance of the coefficient is established by T value. How you will calculate T value? T value is nothing but the slope coefficient divided by the standard error. Okay, that will give us the T value calculated. Okay, and then we have to compare that with the table T value. And then the T cal, that is T value calculated, should be more than the T value of the table. If the standard error is more, then T cal will be less. For example, you see if the coefficient is 0.01 and if the standard error happens to be 0.1, then when you divide 0.01 by 0.1, then the T value will be very less than 1. If it is less than 1, obviously we know, right? Thumb rule. It won't be significant even at no, 15 or 20% level of significance, right? Something like that. So here, the standard is nothing but the deviation of the observed values from the regression line. So this is what is standard. Then standard deviation is what? How much a given data is spread out from the mean. We have a data, and then you estimate mean. Then we have we have individual observations. So how much the individual observations they spread out from the mean. That is what is standard deviation. Especially in case of population, we can say when you have the population data, we can go for standard deviation. In the case of sample data, when we have to do regression, we usually go for the standard error. Okay, so this is what we know: error term, standard error, and standard deviation. So now let us go to the practical part of it. In practical part, what we have is, just a minute. In practical part, okay. Yes, I feel you're able to see the screen. Okay, let me enlarge it. Okay, now it is more clear, it seems, right? Here this is the y variable, you know, yield. We have one attribute, yield attribute, or we can take any macroeconomic indicator like GDP per capita, population. Okay, then this is the time period. Okay, this is log of y. We have taken not log based step, right? So we have to say log, log, right? If you're in natural log, simply go for this is natural log of y. Okay, you should be sure what you're using. Okay, see ln log. You select this value. That's it. So this is the natural log of the value, and this is the log based gen. Okay. Now you see anti-log. So if you take anti-log, for example, in the case of natural log over here, go for exp. So exp, select this value. What you have is you return to the original value, right? So this is the anti-log. In this way, using exp function and MS Excel, it may enlarge it further so that you can see. I think you're able to see, right? Okay. Using the exp function in Excel, you are able to find, okay, using the exp function, you are able to find the anti-log. Now, in the case of log based gen, what we can do, how to find the anti-log. So POWER, power, or power, then the base is 10. The number is this one, right? You see, we have the original value over here. So using exp, we can take the natural, we can take the anti-log of the natural log, and then using power, we can take the anti-log in the case of log base 10. Now the thing is, you see, using logest function in Excel, we can use logest, logest function, which will help us in estimating anti-log of log b. What is anti-log of log b? Just a minute. Okay, yeah, fine. Anti-log of log b is what? So we run regression. So in regression, what we have is, since that is log-lin, so we'll be taking log, for example, this one, you know, log y. This has different variable, and this has your independent variable. So we have to, in Excel, we can go for data analysis package. In data analysis, we can select regression, and then in y, what we have is, we have this one as log y. You see, I'm also selecting label, right? Then you click on here. So label, click here, your second label, and then you go for, okay, I think I have taken, okay, time, right? So this is what is X. So this is your C1, C11. So this is C, right? The dependent variable. X ranges B1 to B11, right? And label the output range. Where should I have the output? Okay. I think this place is sufficient for me to have the output because I got other values as well. I'll go over here. This is more than sufficient for me. Okay, right. So this is where I want my output. Yes. So now you see. So this is the slope coefficient which I have obtained. 0.013275. Now let me take anti-log of it. So since what I have done over here, I think I have taken the log based thing, right? So let me POW here, we go for power, then 10 over here. 1.01309, right? Using regression function, we have estimated the slope coefficient beta 2, like I explained to you with the help of the previous slides. And then what I have done is I have taken the anti-log of the slope coefficient. I'm getting 1.039. Now you see over here, the same value you're getting just using logist, logist in Excel. what I've done is, if you click on here, you see logst largest function, and then I've taken all these values. It is giving you antilog of log b. That's it. Without doing regression in Excel, we obtained it. Okay. Now we know the formula, right? So since we have antilog of log b in the case of largest function in Excel, so this one antilog of log b, minus 1 into 100. That's it. We obtain growth rate. So this is the 3.10 yield of what? Let us say yield of groundnut. Okay, average yield of groundnut in Junagadh district of Gujarat. So we have a growth rate of 3.1% per annum, right? So in Junagadh district of Gujarat state, the yield of groundnut reveals a growth rate of 3.1% per annum over the time period. For example, if it is 2016, so over the time period from 2016 to 2025, let us decide the future also. Chalo. Okay, so this is the growth rate per annum. So 3.10% per annum. That is a growth rate in case of groundnut over the time period. Okay, now if this growth rate is, whether this is significant or not, that we have to see, right? So we have to estimate the precision of the estimates, right? So here what we have done is, usually this is the case what you do, students, right? So here we have standard error, but you see how we have estimated standard error. We have used STEYS function, that is standard error of y given x. Okay, this is of the linear regression estimates where we'll be predicting y using x. Okay, in linear regression, we'll predict y using x. So here STEYS, standard error of y given x. Okay, but this is not the standard error of growth rate. As I was telling you in the previous slide, okay, we have to estimate the standard error of growth rate. But here what we have done, we have estimated the standard error of y given x in the case of linear regression where y values are predicted using x values, right? So this is giving us one standard error. No issues, chalega. Okay, then what we are doing usually, we are taking the t-value because we know how to obtain t-value, right? In t-value, the slope coefficient divided by the standard error will give us t-value, right? You know it, right? So we modified in the case of growth rate, we have the growth rate value. That growth rate value should be divided by the standard error of the growth rate to give us t-value. And here what we have done, you see, we have taken the antilog of log b and then we have divided by the standard error of y given x. And then we are getting a t-value of 10.74. 10.74 is a t-value. Okay. So now let us see whether this is significant or not. Okay, even though this is wrong way, right? Now you understood, right? So what we have done is, in the case of this one, t value, which is calculated, what we will do is, so tcal stands for calculated t value. What we do is equal to the slope coefficient divided by the standard error. Okay, so this will help us in getting the t-value. Okay. So according to what you have done is, here you could see, so antilog of log b divided by the standard error. So the standard error operand is not applicable, as well as this one, the antilog log b, and we are getting a t-value of 10.74. This is the calculated t-value. Now we have to get the table t-value. Table t-value. How we can get this table t-value? We can use a simple regression formula, TINV. So TINV. Now it will tell us the probability as well as degrees of freedom. Okay. We know what is the degrees of freedom, right? N-2. We have 10 observations, N-2. So it is 8. Okay. Then probability. So the probability is, we can say 1%, 5%, 10%. So in 1%, what is the probability? 0.01, right? So 0.01, then 8. 3.35, then TINV, what we have is the probability 0.05, then 8. Then TINV 0.10, right? Or 0.1. This is 10% level of significant, right? So probability, right? 10, 0.1, then 8. So this is the 1% level of significance. This is 5%, and this is 10%. Now you could see here, the value is 10.74, right? And here we could see we are able to reject null hypothesis at even 1% itself. Forget about 5%. We are rejecting null hypothesis that the growth rate is not significant at 1% level itself. So we can say this growth rate of 3.10 of groundnut yield in Junagadh district per annum over the time period is significant at 1% level. But is this right? No, this is not right, because as we have seen, we have obtained growth rate. We need to obtain the standard error of growth rate. Then only we can say whether the growth rate is significant or not. Okay. So then how to do that? It's a tedious process, but it's worth of your time. Now you see, simply just we have to use the formula. The formula is given to you. Okay, then in the formula, you just have to estimate values, and then you have to incorporate. That's it. Like this is given to you yield, and we also know time also. Time is 10 period. Then we know log y. Okay, then this is log y squared, right? And then log y, this is summation of log. This is t squared. Okay, and then we know what beta hat is, and a beta hat is the antilog of log b. Then 100 into beta hat. So we can go step by step. We can solve this one first, and then we can solve the equation over here, and then we can solve this, and then we can solve all these together, and then we can multiply the value with this. That's it. Okay, when you are doing it, then we'll be able to easily finish it. Okay, so like we have gone step by step over here. If you want this Excel file, I can share this with you, no issues at all. See, we have gone step by step. Okay, and then we have solved all those things by just incorporating values. Okay, and then here we have obtained the standard error of growth rate. So 1.089, this is the standard error of growth rate, and this is growth rate 3.10, which you already obtained. Now we are incorporating in the t formula, that is t cal formula. Okay, calculated value of t. So growth rate divided by standard of growth rate. So we have the growth rate divided by standard of growth rate is 2.84. Now, so this is the calculated t value. Now we have the critical t value. We can see here 1%, 5%, 10% level. The value of calculated t value should be more than the critical t value. That is, we know. Then only we will be able to reject null hypothesis that the growth rate is not significant. So here at 1% level, we are not able to reject. In the previous case, the t cal, that is calculated t value, was something around 10.74. That was huge value. And we were able to reject null hypothesis at 1% level itself. But here we are able to reject null hypothesis that the growth rate is not significant only at 5% level. So here we could see now that was something like estimate, even the growth rate is more or less the same. Growth rate is same, but the significance of the growth rate is overestimated in the previous case. But here, then you use the formula or the correct formula, then we are able to see that the significance of growth rate is correctly estimated. So overestimation, and here we have correct estimation. So now we can say that the growth rate of whatever the crop is, the groundnut yield, is significant at 5% level. Okay, so growth rate of groundnut productivity in Junagadh is at 3.10% per annum or 3.1% per annum, significant at 5% level. Okay, or at 5% level of significance in whatever you want to interpret. So in this way, you're able to see that we have not overestimated the significance of growth rate. So this is very important. So you try to do this. Okay, you try to use the formula even in your thesis. When you do it right, take growth rate by using log base 10, and then where you can use the formula, all these formulas and all, in which we'll be able to estimate not only the growth rate properly, but also the significance of growth rate. So in this way, you will be able to do it. Okay. So right now, in this class so far, what we have covered is, we have covered the growth rate model, right, first of all, and then we introduced the principle of compounding. Then we understood how to interpret the growth rate model, that is log-lin model. Okay, what is log and what is lin, and how we have to transform the values of y, that is the different variable, observations of y, so that we can use log of it. And then when we introduce the model, then we'll be able to get the slope coefficient. So in our case, beta 2. So beta 2 can be directly interpreted, right? That gives the instantaneous growth of rate. But what we are more interested is in finding the compound growth rate. So that is what the purpose is. So over the time period, what is the growth rate? Compound growth rate. So that now we are just using simple process of taking anti-log of slope coefficient, then minus 1 to 100 is giving us compound growth rate. But our business doesn't stop there. We have to find the significance, whether it is significant or not, precision of the estimates. So we can find significance by using standard error. So standard error is a good tool which helps in finding the significance of the estimates. Now we know what standard error is, Okay, how much the observations are deviating from the regression line, right? That is what standard error is. How much the average distance of observations from the regression line, or how much the observations are deviating from regression line. Like standard error. What is standard deviation? The deviation of observations from the mean, standard deviation. Then standard error is different, error term is different. So error term is also called as residual, which is different because it captures the effect of all the variables which have not been included in the model. That is error term. Now we are clear about all these things, right? Then after estimation, what the students usually commit mistake is, they just find the standard error of the beta coefficient. So for example, you see, what many people will do is, this is the regression output, right? So this is the slope, right? And this is the standard error of B. Okay, if slope is beta for you, this is standard error of the coefficient. Okay, so what we usually do is, we simply go for, so this is the growth rate, right? So the growth rate, just a minute. So this is growth rate now, or the anti-log, right? Anti-log of log B, right? Then anti-log of log B minus 1 into 100. So 3.10, right? So 3.10, people assume this as coefficient, and then they use this standard error, right? So now you see 3.10 divided by 0.04, 676. Or simply we can use this coefficient, or you forget this is over, now we are going over. What we can do is 0.13 divided by 0.04. You see what we're getting? T stat. Okay, now this T stat is significant, right? At what level? You could see, for example, T I and V, probability of 0.05, then degrees of freedom is 8. 2.30, right? If you go for 1% level, then T I and V, probability of 0.01, then degrees of freedom is 8. So you could see clearly now this is significant only at 5% level, okay? Or you can look at the p-value. The p-value range is 0.02. So the value lies between 0.01 to 0.05, 5%. So we can see. So just by dividing the coefficient of and by standard error, or getting p-value of this, people used to say that growth rate is significant at 5% level. Again, this is wrong, because this is not the standard of the growth rate, because this is standard of the beta coefficient which you obtain in this regression model. Okay, so we have to obtain the standard error of the growth rate that can be obtained only by this simple though tedious formula. It's since we are not able to drag this. Okay, if you are really confident of using Stata, we can, you can develop some file. Okay, using Python or in Stata, using Hadoop file. Now you can construct a file. We know how to obtain the standard of growth rate now. If some file is constructed, or even in Python, if you are familiar with Python, if you're able to construct a file where we'll be able to easily get the standard growth rate in one step, we can, just like we are getting growth rate in one step. Now you see, we are getting growth rate in simply LOGEST, logest formula. So logest, then minus 1 to 100, we are getting growth rate. In next line, we can easily get standard growth rate, provided we have a function like it. If you're able to have a function, even Excel, we can do it. If you're able to do this, if you understand Excel properly, you can easily do it. And if you do it using some macros or something like that, then you can easily have it. With this, I think we are clear about the log-lin function. Hope you also understand the practical part of it, where you can even easily estimate the not only the instantaneous growth rate, but as well as the compound growth rate, right? So in instantaneous growth rate, you could see here the beta coefficient, what you're getting, it is 0.013, right? So if x increases by 1 unit, then y increases by 0.013 into 100. 1.32 percentage per annum. That's it. If x increases by 1 unit, the y increases by 1.32 percentage. This is what instantaneous growth rate is. But if you could see compound growth rate over the time period, we have 3.10% per annum increase of y variable over the time period. Okay. Hope the class was good for you and you would understand something in a better way. Okay. So thank you for your time. We'll meet again tomorrow and bye for now.